Hello and welcome back to Hilbert Spaces, the video series where we talk about infinite dimensional spaces that have a geometry given by an inner product. And indeed, in today's part 17, we will talk about the famous Riesz representation theorem. This one is really important because it tells us how linear functionals look like in Hilbert spaces. So you see, this is our first step into operator theory for Hilbert spaces. However, as always, before we go into the details, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, as a supporter on Steady, you can download a lot of additional material with the link in the description. And now, without further ado, let's immediately clear up what we mean when we say functional. And as often, the general assumption is that we have a Hilbert space X, and this can be a real vector space or a complex vector space. And in order to unify both cases, we just say that we have a Hilbert space over a field F. This is important because now we will consider mappings from X into F. More precisely, these will be continuous linear maps, also called continuous linear functionals. And usually, to keep it short, we just call such a map L a functional. So you can remember here, the input space is possibly infinite dimensional, but the output space is just one-dimensional. And moreover, please recall that for a linear map, being continuous is equivalent to being bounded. And in this context, bounded always means that the operator norm of L is a finite number. And in order to calculate this operator norm, you need to use the norm on the left-hand side and the norm on the right-hand side. More concretely, we take the absolute value of L of x, and then we go through all x which have norm 1 in x. And now what we want is that this supremum is always a finite number. So the linear functionals we consider here are always bounded. And in order to explain this whole definition a little bit more, let's immediately look at an example. So for example, a nice infinite dimensional Hilbert space is given by the sequence space L2. And there the index set for the sequences is given by the natural numbers n. Hence, a linear functional L would get a whole sequence xn as an input. However, the output has to be a scalar, and this one can be reached by combining some of the sequence members. So for example, we could take x1 plus 2 times x2. And this is clearly a linear map into F, so we just have to show it's also bounded. Hence, we just have to calculate this operator norm, which means we have to estimate this absolute value of L of x. And this is not complicated at all, because L of x is just x1 plus 2x2. Therefore, we just have to use the triangle inequality for the absolute value to get our estimate. So we just have the absolute value of x1 here and the absolute value of x2, but we already know that the L2 norm of the whole vector x is equal to 1. And this immediately implies that a single component cannot be larger than 1 in the absolute value. Otherwise, the whole L2 norm would also be greater than 1 in this case. So we don't have to calculate much here, because we immediately see that the whole supremum here has to be less or equal than 3. In particular, it's finite, so we have a bounded linear functional. On the other hand, we also see that we can easily rewrite this linear functional by using the inner product in X. Namely, if you remember the standard O and B we have in L2, then we can use E1 to describe our first component x1. Indeed, E1 applied to X gives us the first component of X. And the same with E2 gives us the second component of our sequence X. Therefore, the whole linear functional can be described by E1 plus 2E2. So this is the element on the left in the inner product, which completely determines L, because on the right hand side we only have our X. You might have already seen something like that in an informal way by writing that L is equal to this left hand side. And of course, this makes the whole linear functional much easier to deal with, because it's just represented by a single vector in X. And in fact, each bounded linear functional defined on X can be represented in such a way. And now you might already guess, this is exactly the statement of the Riesz representation theorem. So you immediately see this is an important and nice result which holds in any Hilbert space. So the assumption is the same as before. We have a Hilbert space over a field F and a linear bounded functional L. And now the conclusion is that this functional is represented by a vector y in X, and this one works in a unique way. So we have existence and uniqueness for this element y. And moreover, the claim is now that L of X is equal to the inner product y with X. So X is still our variable here, but y is fixed by our linear functional L. And in addition, we also get that the operator norm of L is exactly given by the norm of y in X. So you could say that this representation also conserves the norm. And that's it. This is the whole Riesz representation theorem, and as you can see, it just tells us that every bounded linear functional can be written as such an inner product. So we get the information that all continuous linear functionals have this simple form. And in fact, the proof of this statement is not so complicated because we can use the orthogonality in our Hilbert space. However, before we do that, please first note that the kernel of a continuous linear map is always a closed linear subspace in the Hilbert space. This is helpful because it means we can easily use the orthogonal complement and we can use it again afterwards. And now if we assume that the orthogonal complement is just given by the 0 vector, then we know that the orthogonal complement of that is the whole space X. Simply because of the fact that every vector is orthogonal to the 0 vector. And since we have a closed subspace here, we know that the double orthogonal complement is the original space again. So we definitely have this implication for the kernel of L, and we can also go vice versa. So please keep that in mind. If the kernel is not the whole space, the orthogonal complement cannot be trivial. And exactly this fact we can now use in the proof of the Riesz representation theorem. And indeed, we will start with the existence part, so we will show that we can always find such a vector y. And let's immediately discuss the first case where the kernel is the whole space X. This is the trivial case because it means that we actually have the 0 map for our linear functional L. Which means y is equal to 0 already satisfies everything. Therefore, the actually interesting one is the second case where the kernel is definitely smaller than the whole space X. And by what we have said before, this one also implies that the orthogonal complement of the kernel is at least one-dimensional. The 0-dimensional case is simply not possible. And there maybe a sketch can be helpful. Here we have the whole space X. And inside we can find the kernel as a subspace, and we know it's not the whole space X. Moreover, even more importantly, we also know that the orthogonal complement lies in there as a subspace, and it is at least one-dimensional. Indeed, the kernel will be a high-dimensional subspace, because if we have a high-dimensional Hilbert space, we still map into a one-dimensional one. And if you just take linear algebra for the finite-dimensional case, you know that we have the rank nullity theorem, which tells us that the dimension of the range plus the dimension of the kernel is equal to the dimension of the input space. So roughly speaking, the dimension of the kernel is really close to the dimension of X. However, now in any case, we have the guarantee that we can always find a vector z which does not lie in the kernel of L. Which also means that if we want, we can scale it down to the length 1. The orthogonal complement of the kernel is a subspace, so we can always do that. And now what we can also do is to put this element z into our linear map L. So we definitely know we get out a complex number here, but it cannot be 0. And now I want to use this output in the complex conjugation as a new scaling factor. So we just scale z with this number and we get out a vector which is non-zero. And there I can already tell you, this non-vanishing vector is exactly our y. And in order to show that, we just have to calculate this inner product to see that we get out L of x. So we have y with x in the inner product, and now let's substitute y. So instead of y, we now have to deal with the x vector in the orthogonal complement. And you might immediately see we can just pull out the scalar factor, and we have L of z in the front of the inner product. So indeed, this explains why we wanted to have the complex conjugation for the scalar factor. Okay, and now in the next step, I just want to add a 0 here. So it should look exactly like before, but now in the second component, I want to have a scaled version of z. And also minus x, such that we lie in the kernel of L again. Indeed, if we lie in the kernel of L, then this inner product is actually 0 and we can just add it. However, of course, in order to get that, this lambda factor here has to depend on x. So this is the whole idea. This whole thing here should lie in the kernel of L. Therefore, the only question here is, how can we satisfy that with a given lambda x? And maybe it's not too hard to see, we just put this vector into L and we know it should be equal to 0. And then on the left hand side, we can just use the standard linearity. And now you see, we can simply solve this equation for lambda x because we know L of z cannot be equal to 0. So lambda x is simply L of x divided by L of z. So now we see adding this 0 element before was possible and we can continue our calculation. Namely, now we can just combine both inner products into one. And then we see this x cancels and only lambda xz remains. However, lambda x is just a scalar, so we can simply pull it out. And then the next thing we can use is that we normalized our z vector. So we know that this inner product here is just equal to 1. So we only have lambda x times L of z, but there we already know only L of x remains in this product. And of course, this is exactly what we wanted to show, why x in the inner product is given by L of x. So the existence is proven and we can immediately go to the uniqueness statement. But this is quite simple to show. Let's simply assume that we have two vectors y and y tilde that do the same thing. Namely, they both represent L of x for all x in x. Which means that these two inner products coincide and we can just subtract 1. This implies that we have y minus y tilde in the inner product and this one is equal to 0. And this equation holds for every x in x, so we can also choose a very special one. Namely, for x we can just take y minus y tilde as well. Which actually means here that y minus y tilde has length 0. And since the norm or the inner product is positive definite, we know this can only hold for the 0 vector. Hence there is no choice at all, there can be no difference between y and y tilde. Okay, so you see, existence and uniqueness is given for this y vector. And then finally we can talk about the last statement in the Riesz representation theorem, which was about the operator norm. Namely, the statement here is that this operator norm of L is equal to the norm of y. And now of course we can just use that instead of L of x, we can write the inner product y with x. And since we have this inner product in the absolute value, we can use the famous Cauchy-Schwarz inequality. This one gives us an estimate with the norms of y and x. So in general we have this product of the two norms, but here we already know that the norm of x should be equal to 1. And this immediately tells us that the whole supremum here cannot exceed the norm of y. In other words, we already have shown one inequality out of 2. And indeed, the other inequality for the supremum we can show by just putting in a special vector with norm 1. For example, we can just check what happens when we put in the direction of the vector y, so the normalized version of y. And there we can immediately use the linearity of L and pull out the scalar. So we only have to know what L of y is. And by the representation theorem, this is just given by the inner product y with y. And there we have it, because this is just the norm of y squared. Therefore the result here is exactly the norm of y. Hence this line here tells us that this supremum here is greater or equal than this norm. Which gives us the second inequality, and we actually have the equality as wanted. Which closes the whole proof, and now we have the famous Riesz representation theorem for Hilbert spaces. So now we know if we have a complete inner product spaces, we can represent the bounded linear functionals. And in fact, this is really helpful, especially when we want to consider adjoint operators for Hilbert spaces. And I can already tell you, this is what we will do in the next videos. So I really hope I meet you again and have a nice day. Bye bye.